Okay, so let us now discuss applications of vector calculus. So first of all, we'll study what is Green's theorem. Green's theorem for plane. So whenever we are in a plane, that means in 2D region, in that case, we can use this Green's theorem, and its statement says that if R represents a closed region in the xy plane, so suppose we are in the xy plane and this R represents the closed region bounded by the simple closed curve C. So this is one thing that is given to you. Another thing is that, and let M and N, they be continuous functions of x and y. Which have partial derivatives del m by del y and del n by del x in the region R. So that means we have the functions m and n whose partial derivatives are defined in that particular region. Then according to this theorem, we have the result. It says that integration over the closed curve C of the function m dx plus n dy, this is equal to the double integration over the region R for the quantity del n by del x minus del m by del y dx dy, where what is the region C? The closed curve C, where this C is traversed in the positive direction. So here we are to understand various things. Positive direction means the direction is anti-clockwise. So here what we are given some region in xy plane. Some curve C is also given to us. So suppose this is our x-axis, this is our y-axis. Some region here is given to us. Suppose this is the curve C. So here the direction is taken to be this anti-clockwise direction. Why? Because in this direction this integral is taken to be positive. So in that case, in this particular region, suppose we have a region like this. So this is a region. In this region we have some curve C, and in this region also we have the functions m and n, which themselves are continuous functions of x and y, and their partial derivatives, they also exist. So in that case, this Green's theorem, it says that this line integral is equivalent to this surface integral. So this theorem basically connects this line integral with the surface integral. And if you notice that you already know these terms, m dx plus n dy and del n by del x minus del m by del y, they appear in differential equations where the given equation is an exact equation. So you could remember these quantities in this way. So this is the Green theorem, which is defined for plane. Now we can relate this Green's theorem in plane. So we could relate the Green's theorem in plane with that of Green's theorem in vectors. Now let's see how we can do that and what is the theorem here, right? So for doing that, if I define in the xy plane, if I define the vector r to be xi cap plus yj cap, because we are now in xy plane. So the position of some point P here having coordinates x and y would be given by the position vector r, and whose components would be xi cap, because in this direction we have unit vector I, here we had unit vector j, plus yj cap, right? So this is your unit vector, and so likewise you will have its derivative as dx I cap plus dy j cap. So this is what we have, and moreover, if we define the vector f to be m I cap plus n j cap, where what are m and n? M and n, they are functions of x and y, as we have defined above. Functions of x and y, which are continuous functions and also have partial derivatives, right? So using this, I can now define the vector f dot with vector dr. So what would be this? It would be mi cap plus nj cap dot with the vector dx I cap plus dy j cap. So when you perform this dot product, it would be equal to m dx plus n dy, right? So if you notice, this quantity is same as this quantity over here. So that means in place of this m dx plus n dy, you can now write the vector f dot the vector dr, right? So this is one portion. And if we look at this right hand side, we wanted to have a relationship among this and the vector f. So let's see how can we obtain that. So for that, if you take the curl for your vector f. So what is curl of your vector f? That is the cross product of this del and the vector f. So we know how can we take this cross product. It is I cap, j cap, k cap. The value for del, it would be del x, del by del x, del by del y, del by del z, and according to this vector f, we have defined the vector f to be this. So I can write 0 k cap also. So it would be m, n and 0 here. So let's perform this cross product over here. So that means for I cap, now here notice that this m is a function of x and y. This n is also a function of x and y. Therefore, the derivative of m with respect to z, it would be 0, because there is no z term here, and the derivative of n with respect to z, that would also be equal to 0. So keeping that in mind, when you perform this, when you solve this determinant, you will obtain 0 here, and because when you apply this onto this, you will again have 0. Then you have minus j cap, the quantity this is 0, and then the quantity this is again 0, being this term. And then we have plus k cap. For k cap, we have this quantity, the partial derivative of n with respect to x, and then we have this quantity, the partial derivative of m with respect to y. So that means your curl of f. So curl of f, what is your curl of f? It is del cross vector f, that appears to be k cap del n by del x minus del m by del y, this quantity. Now, because in our Green's theorem we have this term appearing here, so that means we wanted to extract this term from here. So how can we extract this term from here? If you take the dot product of this whole quantity with vector k, so this would become the quantity k vector into del n by del x minus del m by del y dot with vector k. Now you know the k vector dot with k vector is equal to 1. So therefore you have del n by del x minus del m by del y. So this quantity here. So that means the value of this quantity here is equal to del cross f vector dot with k vector. So you obtain the value of this quantity as this. So that means on the right hand side for this Green's theorem, you can write del cross f dot k. So in other words, our Green's theorem in plane, which was written as the line integral over C of the quantity m dx plus n dy, this is equal to the double integral over R del n upon del x minus del m upon del y dx dy has now been converted to, in plane, Green's theorem in plane is now converted to the value integration over the closed interval, closed curve C of this quantity. Now the value of m dx plus n dy that we obtained in equation number 1 as f dot dr. So we write it like here. We have f vector dot dr vector. This is equal to the double integral over r. Now the value of del n by del x minus del m by del y we obtained in equation number 2 as del cross f dot k cap, right? So we have this quantity as this one. So del cross f dot k, right, into dr. Instead of dx dy I can now write dr, where what is dr? Actually dr is your dx dy only. This is just for the writing purpose. So this theorem is now converted from this quantity to this particular quantity, and so we have defined, so this is the Green's theorem in the vector notation. So see, we obtain a beautiful relationship which converts the given line integral to the corresponding surface integral, right? So this is what you obtain from here. So this is the Green's theorem.